Good day everyone. This lecture video is on Unit 3-2, Response Surface Methods. For this lecture, we're going to cover the following topics. First, we're going to talk about the general procedure for performing response surface methods. And then we're going to talk about method of steepest ascent or descent. Okay, so in RSM, we basically deal with a response variable that is known to be influenced by several variables. And the objective is to optimize the response variable. So say, for example, you're looking at the process yield, which is known to be influenced by temperature and pressure. Okay, so we can express this relationship in mathematical form as y equals f of x1, x2 plus epsilon, which is the random error. The expected value of y, therefore, is equal to the function of x1, x2, which could be denoted furthermore as nu. And therefore, this is the response surface. Graphically, it would look something like this with a two-variable model. So we basically plot expected yield versus temperature and pressure. This is the response surface, and this is the corresponding contour plot, which basically shows us the different heights along the response surface. Okay, so these are constant expected yields at different x1 and x2 values of temperature and pressure. Okay, now let's move on to general process for RSM. So again, the goal is to determine the optimum operating conditions or to determine the region where operating requirements are satisfied. Now, in most cases, we don't really know the true functional relationship between the response and the independent variable. Therefore, or variables. Therefore, the first step is to approximate the true functional relationship. Okay, now we then conduct experimental designs to collect the data in order to be able to later on fit a model to this data and approximate the functional relationship between the response and the independent variables. Now this experimental design is called the response surface design, and in what we're going to discuss, okay, and in most cases this is what is being used, we're going to use least squares method to estimate the parameters for the approximating functional relationship. Okay, now in most problems, RSM problems, these two models are enough, no? Enough to approximate the function. So we have the first order model where the response is a linear function of the independent variables, which is of course familiar to you. You can express it as such. So you have the betas as the parameters corresponding to the different independent variables x1, x2 to x sub k. And we have also the second order model, which is used when there's a curvature in the system. Okay, and this is how a second order model generally looks like. So you have the linear terms, you have the quadratic terms, and then you have the interaction terms. A note on this, so you in most cases, okay, if you're still far from the optimum region, okay, a first order model is usually adequate. Now once this is not adequate, okay, and you have to proceed to approximating the true functional relationship using a second order model, then that is an indication that you are in the optimum region. Okay, so then the next step after approximating the true function is to determine the region of the optimum. Okay, and after finding that region, okay, you refine the approximating model by conducting further experiments and fitting a more refined model. Okay, so say for example a higher order polynomial model, and then you analyze the model. Okay, so as you might expect, is the performing RSM is sequential in nature. So suppose that this is this represents, okay, the region of operability for the process. And these are the contours of constant response, all right? Usually we start at the point where we have the current operating conditions. So say, for example, that we are trying to maximize the response, no? We start from this point, and the objective is basically to move to this direction, okay, so that we can reach the region of the optimum, okay? So we want higher, okay, the highest response, okay, the highest response possible. So we want to determine the values of the independent variables that will allow us to get that maximum response, okay? And we would find that in that region. Now, the challenge is for us to get from here to here in the fastest way possible. So we want a simple and economically efficient path to that optimum region. All right. Now, when we are far from the optimum, as I mentioned earlier, the first order model is usually adequate. Okay, so we want to move to the optimum region in the simplest and most economically efficient way. So now let's talk about method of steepest ascent. Okay, so the method of steepest ascent is basically a procedure for moving sequentially towards the direction of maximum increase in the response. So you call it descent if you are aiming for minimum increase. All right, so graphically, we show that here, so say for example, this is the current operating conditions, okay? And this is where we have our first fitted first order response surface, okay? What we want to do basically is to move from this, okay, towards the direction where we could get a response that is the highest. And as you can see here, given the contours, okay, so this is a first order model, therefore we can see parallel lines here, okay. So currently, we are at the region where our expected response is 20, okay. So we want to move towards this direction where we could get to the point where y hat is equal to 50. Okay, and the path of steepest ascent is a path that goes through the center of the design space and perpendicular, okay, perpendicular to the surface. Okay, and this is where, so the path of steepest ascent is where the response increases most rapidly. And you achieve that, as I said, by moving perpendicular to the fitted surface. Okay, so this shows you the general algorithm for method of steepest ascent or descent. Okay, so first we fit a first order model, no? So the first approximating function, and it's usually the first order model. Okay, so if it is still adequate, okay, then we start with the movement, okay, through the path of steepest ascent. Okay, so we move a step along the path of steepest ascent. And until when do we do this? So basically, until you can observe, okay, an increase in the response, if we're talking about the method of steepest ascent, okay, which means that we are trying to find for the maximum response, okay, or if there is still a decrease in the response in the case of a problem where we're looking for the minimum response, okay. So as long as there is still a change, okay, so increase or decrease, then we continue moving along the path of steepest ascent or descent. Once we observe that there's no longer an increase or decrease, then we have to proceed to finding a new first order model, okay. Now, if a first order model is still adequate, then we go through the same procedure. Otherwise, then that means that we're already in the region, okay, of the optimum, and we therefore want to fit a second order model or higher order polynomial. But in most cases, a second order model would be enough. Okay, and then from this, okay, we locate the stationary point, okay, where we could find basically either the maximum or the minimum point. Okay, and then that's the end of the method. Okay, so let's illustrate the first part, okay, of the method of steepest ascent, where we try to fit a first order model. Okay, using this chemical process yield example from Design and Analysis of Experiment by Montgomery. A chemical engineer is interested in determining the operating conditions that maximize the yield of a process. Two controllable variables influence process yield, namely reaction time and reaction temperature. The engineer is currently operating the process with a reaction time of 35 minutes and a temperature of 155 degrees Fahrenheit, which results in yields of around 40%. Because it is unlikely that this region contains the optimum, she fits a first-order model and applies the method of steepest ascent. The engineer decides that the region of exploration for fitting the first-order model should be 30 to 40 minutes of reaction time and 150 to 160 degrees Fahrenheit of reaction temperature. Now, to simplify calculations, variables will be coded to the usual -1 to 1 interval. Okay, so we let the natural variable for reaction time and reaction temperature be time and temp respectively. So x1, therefore to determine the values of the coded variables, we use the following equations. X1 is equal to the quantity time minus 35 all over 5. And then x2 is equal to the quantity temperature minus 155 over 5. Suppose that these are the response y, or the process yield, observed with corresponding to these values of the natural variables, time and temperature. Okay, so we then convert the natural variables to the coded variables as such. Okay, and you can see that this is a 2 to the 2 factorial design augmented by 5 center points. Okay, 5 center points. And the center point basically is the current operating condition. We use the center points because it allows for three things. So the first is to obtain an estimate of the error, and then it also allows for checking for interactions in the model and for checking for quadratic effects. And of course, we want to know this because we want to verify that we're not yet in the region of the optimum. Okay, so first, because we have the center points, you can obtain an estimate of the error. Okay, so sigma hat squared is equal to the sum of the squares, okay, of the response variable, okay, at the center points, okay, minus the square of the sum of the observed responses divided by 5. Okay, and all of this divided by 4 because we have a 2 to the 2 factorial. And this is equal to 0.0430. Okay, now we also are able to check for interaction using the center points. So again, the fitted first order model using the usual method for analyzing 2 to the 2 factorial models. And then using the regression model as shown here, okay, as an empirical model to represent the findings from the 2 to the 2 factorial design, okay, you have here the fitted first order model. Okay, so y hat is equal to 40.44 plus 0.775 x1 plus 0.325 x2. Okay, now checking for the interaction, we investigate beta hat 1, 2, okay, and we obtain this, remember, by getting one half of the effect estimate, okay, for interaction between temperature and time, okay, and that is equal to -0.025 0.025, okay? And therefore, the sum of square of interaction, which can be obtained by getting the square of the contrast divided by 4 is equal to 0.0025. Now, we get the F statistic, okay, which is equal to the sum of square of the interaction divided by sigma hat squared, and this is equal to 0.058. So since this is very small, okay, then we can conclude that the interaction is negligible. Okay, now checking for curvature, okay, these parameters correspond to, so beta 11 hat plus and beta 22 hat correspond to the square of the first independent variable x1 and the square of the independent variable x2 respectively. So if we add this to the model, then we would have a second order model. And therefore, we want to check, okay, for the significance of the coefficients for these terms, okay? And this, okay, beta 11 hat plus beta 22 hat is also equal to the mean of the responses from the factorial part of the model minus the mean of the responses from the center points, okay? And this is equal to 0.035. A negative 0.035. Now, we want to test the null hypothesis that beta 11 plus beta 22 is equal to 0. Okay? If we reject this null hypothesis, then that would indicate that there is a significant curvature in the model. Okay? So, the sum of square of a pure quadratic, okay, pure quadratic, is equal to NF times NC times the quantity YF bar minus YC bar squared all over NF plus NC. So NF is just the number of observations for the factorial part, and then NC is the number of observations for the center points. Okay, and since SS pure quadratic is now equal to 0.0027, we can compute for the F statistic. Okay, so this is equal to 0.0027 divided by the sigma hat squared, which is 0.0430. And as you can see, since our F statistic is very small, then we can conclude that there is no indication of pure quadratic effect. Therefore, the first order model is still adequate. Okay, and the analysis of variance is summarized in this table. So as you can see, the interaction as well as the pure quadratic are not significant based on the p-value, okay, but the model is significant. Okay, so the model is significant and it's still and a first order model is still adequate. Okay, so going back to our algorithm, so we were able to fit a first order model. Okay, it's still adequate. Okay, and so now we move. We try to move along the path of steepest ascent. Okay, so the design center is at x1 equals 0 and x2 is equal to 0. Now, based on the model parameters, there is a 0.775 unit movement in the x1 direction for every 0.0325 unit movement in the x2 direction. Therefore, the path of steepest ascent goes through x1 equals 0, x2 equals 0, with a slope of 0.325 over 0.775, which is equal to 0.42. Okay, now suppose that the basic step size is 5 minutes of reaction time based on process knowledge. Then delta x1 is equal to 1 and delta x2 is equal to 0.42. Okay, so given that, we can now perform, okay, the response surface design, okay, or the experiment to be able to move through the path of steepest ascent. Okay, so our origin is 0, 0. Okay, in terms of the coded variable, origin is 0, 0, and then the delta is 1 for x1 and 0.042 for x2. Therefore, origin plus delta is 1 and 0.42. Origin plus 2 delta is 2 plus 0.84, and so on. Now, of course, when we conduct the experiment, we have to transform the coded variable in terms of the natural variables, okay? So these are the corresponding values of the natural variables, and suppose that these are the observed responses given these steps through the path of steepest ascent. Okay, as you can see, as you can observe, no, from this point onwards, the response is increasing. However, at a certain point, okay, at this point here, okay, the response starts to decrease. Okay, so again, as long as the response is increasing, since we're dealing with a, we want to maximize the response here, then we just move along the path of steepest ascent. As soon as it decreases, then we proceed to fitting a new first order model. Okay, but before we do that, let's just look at the behavior. So as you can see here, we're still going up. Okay, so it's like climbing a hill, and then at this point, we see that there is a decrease in yield. Okay, so now we fit a new first order model. Okay, and now our new base is at 85 minutes and 175 degrees Fahrenheit. Okay, so that is now the new design center. X1 is equal to 85, X2 is equal to 175. And so now the next region of exploration is 80 to 90 minutes. Okay, and then for temperature, it's 170 to 180. Okay. So again, we have a 2 to the 2 factorial augmented by 5 center points. Okay, so these are the values for the natural variables. And to make it easier computationally, we code the variables. Okay, so we have x1 and x2 here. x1 is equal to this, x2 is equal to this. This is time and this is temperature. Suppose that these are the responses that we observed given at these treatment combinations. We now obtain another fitted model using the usual method for analyzing 2 to the 2 factorial design, okay, and representing the findings using a regression model as shown here. Okay, so, and this is the ANOVA, okay, summary of the ANOVA. As you can see here, okay, the interaction and the pure quadratic, okay, are significant, which indicates that the first order model is no longer adequate to characterize the region, okay, of the system that we are in. So our p-values are small, signifying significance of the interaction and pure quadratic, and therefore the first order model is not an adequate approximation of the system, which also indicates that we're in the region of the optimum. Okay, so going back to the algorithm, the first order model is now not adequate, therefore we proceed, okay, to fitting a second order model. So we proceed to coming up with a so we conduct another experiment and fit, okay, a second order model. Okay, but before we do that, okay, let's just go through the general algorithm for determining coordinates of a point on the path of steepest ascent. Okay, so there are three general steps. The first step is to choose a step size delta x sub j in one variable. And under this, you basically select the variable that you know most about, or select the variable with the largest absolute regression coefficient. The next step is to determine the step size delta x sub I in the other variables. Okay, so delta x sub I is equal to beta I hat divided by beta j hat divided by delta x sub j, where I is equal to 1 to k and I is not equal to j. And the last step is to convert delta x sub I to the natural variables, because you're going to conduct the experiment. Therefore, you have to know these values. Okay, so let's go back to the example on the chemical process yield using the first fitted model, which is y hat equals 40.44 plus 0.775x1 plus 0.325x2. So as you can see here, x1 has the largest absolute regression coefficient. Okay, and say that based on process knowledge, step size is 5 minutes. Okay, therefore, delta x1 is equal to 5 divided by 5. Okay, this is equal to 1. Now, the next step is to determine the step size, delta x sub I, in the other variable. So we have another variable, x sub 2. Okay, and this is equal to beta hat 2 divided by the quantity beta 1 hat divided by delta x1. So this is equal to 0.325 divided by 0.775 divided by 1. And therefore, delta x sub 2 is 0.42. Now we have to convert those to the natural variables. So the step size, the step for time is 5 minutes, and the step for temperature is 2 degrees Fahrenheit. Okay, so that's it for this video. In the next video, we're going to talk about second order model fitting and analysis.